13.975.
And then that's for 10 oscillations of 1.3975 seconds is our predicted, or sorry, that's our experimental period. And let's figure out what our prediction is. All right, I know K, my mass, so omega is the square root of K over M. So that's the square root of 1.815 divided by my mass. My mass is going to be my effective mass here, the 0.046 plus what I added to it, which is 0.05 kilograms. So this should be 0.096 kilograms. So we end up with an angular frequency of
4.348
units.
radians a second.
My frequency
Is
0.23 hertz.
0.23.
Is it 1 over?
It's this divided by 2 pi.
Oh.
0.692.
0.692.
Now my period, that's the 1 over.
Oh, I've lost it now.
1.445.
We had 1.3975, we have 1.445. We can find our percent error, since we have a prediction here. So definitely a lot closer than we were before. So 1.445 is our prediction, minus 1.3975 divided by the prediction, 1.445. About 5%. Hey, not bad. I'm pleased with that. Did not work perfectly, but now, more formally, what we would need to do is come up with the spring constant based upon more than just one mass we stuck on it. So we would do several masses, figure out how far it stretches, come up with a graph of position versus mass, figure out what the spring constant is from that. And so we have to have a more accurate value for this. Timing 20 oscillations might work better than timing 10 oscillations. But probably, yeah. And our masses here, if we actually figure out what the actual mass was instead of trusting the manufacturer, might get a little bit closer. Things that in theory would chip away at our 3% off. Questions to hear? All right. Next step. Now, if I wanted to actually come up with an equation for this, I'm going to do a crude estimate here of how far it stretches. So putting 0 there, if I took that off, that's about 23.5 centimeters. So my position, 23.5 centimeters times the cosine, since I started at 8, you can actually put it on there. So if I pushed it up and let go, cosine of omega t, we figured out omega was 4.348 radians per second times time. Phase shift of 0 if we started timing at the point I let go. Meters is so much cooler, so 0.235 meters cosine 4.348 radians per second times time. What's my maximum speed? What's my velocity versus time graph going to look like? Or what's the equation for velocity versus time?
Amplitude, omega, sine.
All right, so what's 0.235 times 4.348? Units?
Meters. No, amplitude.
We did the amplitude times the angular frequency. We did 0.235 meters times 4.348 radians per second.
Meters times radians per second.
That is not a wrong unit, not traditional, but that would be acceptable. However, generally when you multiply something times radians, you don't write the radians, so just meters per second.
Just meters per second.
Which makes sense, we're dealing with
Oh,
velocity,
yeah.
the amplitude is in meters per second. So my maximum speed is gonna be 1.022 meters per second. That's my maximum speed. It's the amplitude. My acceleration, well, we do it again, it's gonna be negative something cosine of 4.3, it's like I lost some stuff there for a second, that's fine. 4.348 radians per second times time. And again, when we go to the slope of the slope, or the slope, it's this times omega, so that times 4.348, which is presumably 4 point something. Oh, okay. Units?
Meters per second squared.
Yep. So using the equations here, we can come up with our maximum speed and our maximum acceleration, or the magnitude of the maximum acceleration. We also, my maximum acceleration occurs when I'm at the extremes, when the net force is in balance the most. So if I took my spring constant right there, 1.815 newtons per meter, and when I'm at the extreme, 0.235 meters, because that's my amplitude there. So when I have this up to here, in theory, it's the spring constant times how far I've displaced it. That should give me what the force from the spring is.
.427
Newtons.
newtons.
Divided by the mass of point really the effective mass, 0.096. Wait, how much we bring into this? We brought in omega with the effective mass, so, yeah.
Was it 0.46?
What do we get?
It was 0.66, not 0.96.
Oh, no, the effective mass plus what I had hanging on it,
Oh.
so that is 0.96.
Sorry.
And we end up with 4 point something.
448.
448.
Meters per second squared, which is pretty darn close to what we had right there. We're off by 4/1000ths of the meter per second squared. Maximum speed, we could have found maximum speed using conservation of energy. Now, because of time, I am gonna point out one thing here. When we plugged into F equals ma, comes from F equals ma. I did the force from the spring divided by the mass. I ignored the weight. On purpose. So, I guess that will be on Thursday, when we talk about why I ignored the weight. It all depends upon what reference you're gonna use. It's a long boil, we'll wait. See you tomorrow. So you're doing that, so slope's going like that. You're trying to find the maximum speed the car can go. So it's gonna go faster and faster and faster until it slows. So if I'm looking at a maximum speed, we're looking at a point just before it slides off the ramp, between restrictions actually down the ramp. If I ask for minimum speed, so it doesn't slide down the ramp, it's minimum speed that your section is right.
Oh, okay, sorry. That's easy, right?
Yes.
Is it possible for you to, after you relay that, email me my contract?
Yes.
You want me to remind you?
Yes.
Okay.
Thank you.